So this is the second video on two-body problems. Previously we did what we call the Atwood machine. So if we have two masses over the pulley, it looks like that, and we did some work. Before the two-body problems, we did some questions with inclined planes. And so now we're kind of putting these things together. We've got an inclined plane, and the angle here is 30 degrees. And mass number 1 is on there. A string is tied to it, and there's a pulley, and then that's attached to the hanging mass. So perhaps, well, just to keep track of these things, mass number 1 is 2,500 kilograms. Mass number 2 is 4,000, and it does say that it is frictionless, so I'll just put in mu is equal to 0. Okay, so we're going to do the same approach that we had before. We're going to figure out the acceleration and the tension. And the first part we're going to do is we're going to think about the system here. So we're going to use the system idea. In other words, what is the F net of the system? And then the mass of the system will be equal to these two added together, which I guess is 6,500 kilograms. And then we're going to go and say, okay, so A is equal to F net over M. So let's think about what could the F net of the system be. Well, when we start putting together all these force diagrams, if we start with M2, it's kind of easy. We'll say, okay, here we got FG2 downwards, and we have a tension force upwards. Over here, we're going to have a tension up here. These two tensions are going to be equal. And now let's think. In the past, we might have put a force of gravity downwards, but after our inclined plane question, we would probably be thinking, okay, here is FG perpendicular, and down the inclined plane here is FG parallel, and then up this direction is going to be the normal force. Okay, now let's consider which ones will be canceling each other out when we look at it in terms of a system. Well, first of all, the two tension forces here, those will be canceling each other out because they're internal. And they're going in opposite directions. The FG perpendicular and F normal are going to be canceling each other out inside of, when we just think of mass number 1, it's pretty clear that they're going to be canceling each other out. So the real question is here, who's going to win in this epic battle between our FG2 and our FG parallel? Okay, so we'll say here in our F net of the system, FG2, actually I'll do FG parallel first because it's on the left hand side, versus FG2. And I'm wondering which one's going to be bigger, because if FG2 is bigger, then this will be accelerating downwards, and this block will be accelerating up the block, up the inclined plane. If FG2 is smaller and FG parallel, then it's going to be accelerating upwards, and this will be accelerating downwards. So it's important for us to figure this out so that we know the directions of these two forces. So FG parallel, if you recall, this two lines look to me like a slide. So I'm going to say FG parallel is equal to mg sine theta, and it's m1g sine theta, and so that would be 2,500 multiplied by 9.8 multiplied by the sine of 30 degrees, and so it gives us a number. It turns out to be 12,250 newtons. Over here on FG2 is just equal to m2 times g, and m2 is 4,000, and when I multiply that out I get 39,200 newtons. So between the two, which one is bigger? Well, here we are. Here we have the winner. So therefore, when we start thinking about which way are things going to be accelerating, if FG2 is greater, then this will be the direction of our acceleration, and we're going to say that is positive, this is negative. This object here will be going up the inclined plane this way, so we'll say that's positive and this is negative. So now when we write our F net statement here, F net of the system, we're going to say that it is FG2, which is positive, minus FG parallel. Oops. So we already have our numbers down here, so it'll be 39,200 minus 12,250, which gives us a net force of 26,950 newtons. And our acceleration, again, it was F net over mass, so that would be 26950 divided by this mass of the system, which was 6,500. And we get an answer of 4.15. And I think there's maybe some more decimals in there. I can't quite remember. Alright, so we're done our first part. We've done the acceleration now, and now it's time to figure out the tension. So maybe I'll go on this side over here, so even switch to green. So now when we're talking about tension, we need to draw some free body diagrams. So looking at object number 1, just kind of recreating it here. It's the one on the inclined plane. So we have, this is FG parallel, and here's the tension force. Now notice, how shall I draw the tension force? Shall I draw it larger or smaller? If this object is accelerating up the inclined plane, that means that this tension force is larger. So I'm going to put a larger tension force here. Here is FG perpendicular, and here is the normal force. Okay, so if I write my F net equals ma statement, and again, this direction is positive, so F net is the sum of all the forces. We're going to have T minus FG parallel is going to be equal to the mass times the acceleration. So if I just solve for T here, I can say T is equal to FG parallel plus ma. FG parallel we already figured out, right, was 12,250 plus the mass was 2,500, and my acceleration was 4.15. Putting those all together, I get 22,615 newtons. Okay, so you'll be getting the sense then for most of these questions. To figure out tension, we can always go and do a check looking at the second object. So the second object was the hanging one, and we had the force of gravity for object number 2 downwards, and the tension force upwards. Now the acceleration will be downwards, so this upwards arrow should be a little shorter. Okay, now we'll get F net equals ma. This was my positive direction, that was my negative direction, so when I expand F net to include all the forces, it'll be Fg2 minus the tension force, which will be equal to mass times acceleration. If I solve for T here, I will subtract, actually what I'll do is I'll add tension force to both sides, and then I'll subtract ma from both sides. So I'll have Fg2 minus ma equals the tension force. Doing my calculations here, Fg2, that was 39,200 minus my mass times acceleration, which is going to give me an answer of 22,615 newtons. So there's my check. Excellent. Okay. So there's our acceleration, there's the tension in the cable. Now, here comes a your turn. I always say U-turn. A your turn question. And I don't know what I was thinking. Really, the your turn shouldn't be any harder than the example we just did. But what did I do? I added friction to it. So I think what I'll do is I'll start the question for you, and then I'll stop about halfway and then let you try to finish it. Okay, so what's different with the friction question, this one and the last one? Well, let's put in all the forces that we did before. So this is still Fg2. This is still the tension force. This is still the tension force. This is still FG parallel, this is still FG perpendicular, and this is still the normal force. Okay, the question is, which way are we going to put the tension or the friction force? So friction force is mu times the normal force, and sure, we can figure that out quite easily. But before that, we have to think, well, where do I add the what do I do for the direction of it? It's the same first question that we had before. My first question before was, which way is it going to accelerate? Right? I didn't know, was FG parallel larger or was FG2 larger? Was FG2 pushing harder or was FG parallel pushing harder? Which way would this entire thing start to move? And even if you look at the wording of this, it says it rests, right? So it's starting from rest and it's going to start moving. So whichever way it's going to accelerate, that's which way it's going to start moving, and then the friction will be opposite the direction of motion. So again, we're going to do this contest here, FG parallel versus force of gravity 2. Okay, so FG parallel will be m1g sine theta versus m2g. Right? I'll put these in again. FG parallel equals this, and over here FG2 equals that one. Okay, so if I plug in the numbers here, I would get for FG parallel 3,500 multiplied by 9.8 multiplied by the sine of 30 degrees, and I get 17,150 newtons. And over here, when I put this in, I get 1,000 times 9.8, so I get 9,800 newtons. Okay, so which one's the winner? This is the winner here. That's a larger force. So first of all, the acceleration is going to be this way. So this will be positive, this will be negative, that will be positive, that will be negative. So once it starts accelerating, once it starts moving, that will be the direction of the motion. And now, when I put in friction, friction will oppose the motion. So now friction will be going this way. Okay, friction will actually be pointed up the same direction as the tension force. So we should put in a little so. FF is up the incline. Had FG2 been larger, then this object would have started to move up the incline and the force of friction would have been the opposite direction. Oh, right. So now that we got that, let me just help you with one more thing here. Let's calculate what this force of friction will be. Force of friction is equal to mu times the normal force. And what's the normal force? Well, the normal force is the same thing as FG perpendicular. So I'm going to say since Fn is equal to Fg perpendicular, that means that this is Fn is going to be equal to mg cos theta. So I'll put it in here, mg cos theta. So if we plug in our numbers, 0.210 multiplied by 9.8 multiplied by the cos of 30 degrees. So now for force of friction, what do I get here? I'll have to check it out. 6,237.98 newtons. Okay, so I'm going to let you try this, your turn at this point now. So continue to do the Fnet and figure out the acceleration, and then go and figure out the tension. So hit pause now and try this out. Okay, so here's my answer. I get an acceleration here of 0.247 meters per second squared. You can see I do my Fnet statement, plug in some numbers, divide by the mass, and I get 0.247 meters per second squared. And then when I figure out what the tension, I do a free body, really messy, but here's a free body diagram of object number 1. And you'll notice in my Fnet equals ma statement, Fnet in the positive direction is Fg parallel, in the negative direction is both force of friction and tension rearranging, careful to solve for t properly, I get 10,047, and I know I do a similar one for object number 2 and I get 10,047 again. Okay, so hopefully you're able to do a little bit of that on your own. Okay, so one last kind of question here, and here's example problem number 4. Just a little spin on the entire type of question here. So here's a cart on a frictionless plane, and we're given one of the masses but not the other mass. So well, okay, let's pretend that we're a student doing this question, and we might say, oh, Mr. Spicer says that the system approach is probably the easier. So let's start with that. Let's think about the system approach, and let's think about all the things we know. I'm going to call this one object number 1 and this one object number 2 perhaps here. So when I think about this, M1 is what I don't know. M2 is 6.1 kilograms. So we're at a little bit of a loss right now because the mass of the system, we're not sure, right? We got M1 plus 6.1 really is what we have. And then if we think about the free body diagram here, so this one will know FG2. Well, we can figure that one out. That's going to be 6.1 times 9.8, so that would be 59.78. It works out to. And then we're told that the tension is 45 newtons, so we've got a tension upwards here of 45, and we know this tension is 45. And so if we're going to figure out the F net of the system, let's see here, F net is equal to, well, the tensions would cancel each other out. This Fg number 1 and this normal force would cancel each other out. So really the F net of the system is just this 59.78 newtons. So my A, which is going to be F net over the M, the acceleration of the entire system is going to be equal to 59.78 divided by M1 plus 6.1. We're at a bit of a dead end here. The problem is we have two unknowns, and we would really like to figure out the mass of the cart, and we can't because we also don't know acceleration. Well, when you get stuck, go back and then take a look at the free body diagrams and try to think of these things as individual objects. So I don't know, let's start sequentially. Let's look at object number 1. Object number 1, let's kind of redraw the free body diagram just to get a sense here. This is the force of gravity of object number 1. That's going to be M1 times G, so it's going to be 9.8 M1. It's kind of as far as we can take that. The normal force is going to be the same, and we're going to have this tension force of 45. We can say F net is equal to MA. F net is going to be just the tension force. It'll be 45 multiplied by M1 times A. Again, we got the same problem, don't we? We have mass and acceleration. We've got two unknowns, right? At this point, some of you might say, hey, Mr. Spicer, let's plug one into that one. Let's solve for A. And then, yeah, and that is a possibility. We could do that. But let's just keep on going and think about our second object here, because I think this is where I've sort of taken you on two dead ends. Let's look at the last one. Perhaps it'll be our gold mine here. Let's see. So we have a downwards force of gravity. We have an upwards tension force. The downwards force of gravity we already found out was 59.78, and a tension force upwards is 45. And we know this mass is 6.1 kilograms. So check this out. If we do our F net equals ma statement, and which way is this going to accelerate? It's going to accelerate that way, isn't it? Because 59.78 is greater than 45. So I'm going to say 59.78 minus 45 is equal to 6.1 times acceleration. Check it out. Finally, we can figure out what acceleration is. If you do this math, our acceleration is about 2.4 meters per second squared once you subtract that and divide by 6.1. So that's kind of neat. Now we go and we say, hey, look at all this work that we've done here. If we want to figure out one of these masses, we can do another one of these questions. So like use this stuff or use this one. So let's use the other object here, and let's say, well, if 45 is equal to m1 times a, and we know that here's the acceleration, right? Here's that 2.4 business. Then we can say 45 is equal to m1 times 2.4. Divide both sides by 2.4, and we get m1 is equal to 18.57 kilograms. And that's pretty cool. And we could even do one more little check over here, and we could plug in the A and the M1 and see if that works for our check. Alright, so there is an example problem number 4 for you. Check it over, and here is your very last your turn, and then you'll be done this video. So alright, so give this question a try, and then hit pause, and then when you come back I'll have some answers for you. Alright, so here's your answer. So first of all, thinking about which direction things are going to accelerate, it's frictionless. The hanging mass will cause everything to accelerate downwards here and left upwards. And so thinking about object number 1, here's our free body diagram. We have a tension force upwards at 24, force of gravity downwards at 29.4. So when we make our F net equals ma statement, we can find out that acceleration is 1.8. Go over to the second object, and here is our free body diagram, and the tension force is really the only force listed under F net, because the normal force and the force of gravity will cancel each other out in this question, and then we get T is equal to m2 multiplied by this acceleration that we found out. Solving for mass, we get 13.3 kilograms. Excellent. I hope you enjoyed this. We'll see you in class.